Well, let's get on with the tutorial where we can actually go into solving a lot of the problems that are set out in the exercise at the end of the lecture notes. We've got these 6 problems, and I will refer to them as I go through the solutions for each of the tutorial problems. So this is tutorial number 9, as per the unit study guide. So looking at question number 1, which is a 100 universal column, 100 millimeter universal column, 14.8 kilograms per lineal meter, is used as a column in a factory. Assuming the column is pinned at both ends and is 3 meters long, using Euler and Rankin-Gordon, calculate the safe load. Now, by now, thus far into this explanation, you'd all know if I said it was pinned at both ends, the effective length of the column is 3 meters. There's no factor that actually is going to reduce that. So getting on to the actual solution of question number 1a, there is our column, pinned both ends, and L equals 1. We've got Euler's formula, which is pi squared EI over KL squared, K being this factor there, 1, and L being the actual length of the column, which is given to us as 3 meters. Plugging that into the formula, we've got pi squared times the Young's elastic modulus multiplied by the moment of inertia, which is given to you. You can look that up in the tables. As I said to you previously in the lectures, you can download one steel or BHP hot rolled steel sections, and where you have 100 UC 14.8, you can read the moment of inertia off directly. All divided by 1 times the length of the column, 1 because it's pinned at both ends, squared. Gives you a load of 250 kilonewtons. So that's what that column could take, the 100 by 14.8 universal column. 250 kilonewtons, we apply a factor of safety of 2. In other words, we divide that load by 2 to give us an actual safe load of 125.05 kilonewtons. But that answers part A of question 1. Question B, we're using the Rankin-Gordon formula. We've got the allowable stress, which is given to us, the yield stress, 300 in this particular case. The area of the section, which you find in the steel tables, 1890 square millimeters. Applying this, the denominator of this equation, 1 plus the little factor A, which is 1 over 7,500 from the information on Rankin-Gordon, multiplied by the length of the column divided by the least radius of gyration, 24.5, which is also found in the tables. That is all squared. Gives you a total load of 189 kilonewtons. Again, we have a factor of safety of 2, which is stipulated in question 1, and so we divide that load by half. So we divide it by 2, and we can put a safe load on there with Rankin-Gordon of 94.5 kilonewtons. And you'll notice that it's smaller than the straight-out safe load for Euler. Reason being that they've taken into account certain modification factors which Euler didn't in using a purely mathematical solution. Now, question number 2 is a timber post, 100 millimeters by 100 millimeters in cross-section, and it is 4 meters long. It's fully fixed at both ends. Over here we can see that, fully fixed at both ends, so the reduction factor for the length is 0.7 from the table 4632, 0.7 times the length. So using Euler then, well, before we get on to using Euler, we work out the moment of inertia, which is purely BD cubed over 12. Being a square section, you could have said 100 to the power of 4, which is the same thing, but it's BD cubed over 12. Gives you a moment of inertia of 8.33 by 10 to the 6 millimeters to the fourth. We use the standard Euler formula, put our knowns into the formula, the E, for instance, the I, and we've got a factor for reducing the length of 0.7 from this diagram, multiplied by the length, all squared, gives you a load of 126 kilonewtons, or 12. Now, 126 kilonewtons would give you a stress in the material if you divided it by 10,000. If you put load over area, 126 kilonewtons divided by 10,000 square millimeters gives you a stress of 12.6 newtons per square millimeter. But if you look at the question, if you look at question 2, it says that the stress is limited to 6 newtons per square millimeter. 6 newtons. So the total load that you can actually put on that cross section is the area of the section multiplied by the allowable stress, and that's 60 kilonewtons. You cannot use this there. I suppose if you divided that by a factor of safety of 2, you might get to something close to this, but still not 60 kilonewtons. But because the stress then is limited to 6 newtons per square millimeter as per question number 2, so we can't stress this thing up to 12.6 newtons per square millimeter. So taking allowable stress times area gives you the allowable load, which is 60 kilonewtons. Allowable stress is 6 newtons per square millimeter multiplied by the area of the cross section, 100 by 100, 60 kilonewtons. So that is the correct solution there. Now, moving on to question number 3. We have a round tube, a mild steel post or strut or column or whatever you want to call it. If it's a post or a strut or a column, it's, in this particular case, it's a compression member. It's got a compressive force on it, and this one happens to be a tube. Now, the moment of inertia computation for a tube is this here. Pi into d to the fourth, the outside diameter, the fourth power, minus the internal diameter, the fourth power, all divided by 64. And you can, if you look up in the correct journals, you'll actually find a variety of moments of inertia for all sorts of shapes. But this is the moment of inertia for a hollow tube. Do you remember we had the previous one? Question number, I forget which one it was. It was one of those in the lecture notes where we had a solid 30 millimeter diameter rod. And that was just pi d to the fourth over 64. Anyway, cut a long story short, you put your outside diameter in, your inside diameter, and you find that you have a moment of inertia for this thing about an axis of 1.688 times 10 to the 6 millimeters to the fourth, 1,688,334 millimeters to the fourth. Using the classic Euler formula, and bearing in mind that this post is substituted for the one we had in question 3, where it was fixed on both ends. Our length factor is 0.7, as it was in question number 2. So we've got pi squared times the modulus of elasticity times the moment of inertia, which we've computed there, divided by the modification factor for the length, multiplied by the length, all squared. And that gives us a load of 425.1 kilonewtons. With a factor of safety of 2, we divide that by 2, and we get a safe load of 212.5 kilonewtons. And that covers question number 3. It's pretty straightforward. Getting on to question number 4, we have a strut which happens to be a universal column which we have to select, which is pinned on one end, fixed on the other end, and the effective length factor is 0.85. And you can check that out by looking back at your notes at table 4632, which will confirm this. So we use, in question 4, we've been given the factor of safety of 3, and we've got to select a universal column. So we've got pi squared EI over KL squared, the standard formula. We make the subject of the formula I by transposing the formula and work out what moment of inertia we need. So selecting from the steel tables a universal column with an I of IYY of 7,010,000 millimeters to the fourth, which is slightly higher than the inertia that we need, we use a 150 UC 37.2. In B, we select the universal column based on its lowest moment of inertia, i.e. YY. So there we have it. That's question number 4. Question number 5 is we're talking about the top chord of a Warren girder. And just to show you what a Warren girder looks like, which I'm sure you all know, it's a girder, it can be a bridge or it can be a truss that looks something like this. You've done examples like this in your solution of trusses. And the top chord, if this is a support there, and there'll be another support over there somewhere, this is the top chord, which is in compression. So each piece of the top chord is a strut, in fact. Now, one of these struts has an axial force of 360 kilonewtons imposed on it. Which is that there. We've got to use a factor of safety of 2 according to the question. Because of the factor of safety of 2, we actually escalate the imposed load by a factor of 2. So we have to design an angle that can carry a load of 720 kilonewtons. Now, P equals the standard Euler formula. We transpose to find IYY. Transpose the formula, and we find that we need a moment of inertia about the YY axis. We take the YY axis, this one over there, because that's the weakest axis, and that's the way an angle will actually buckle when it's under compression. We find an IYY of 0.69 times 10 to the 6 millimeters to the fourth, and if we choose from your tables a 100 by 100 by 10 equal angle with an IYY of 0.696, we have the correct answer. And the area of that angle, of course, is 1810, all found in your one steel notes. So all we did there was increase the load by multiplying it by a factor of 2, which brought us down to the correct answer. Getting on to question number 6, where we asked if this member there was in tension. So instead of it being in compression, it's in tension. So it's not actually a strut, it's called a tie. And given the same material properties and factor of safety, what size of equal angle would be suitable? Well, it's a basic case of stress equals load over area. The load is 360 kilonewtons, as we had in the first problem. Factor of safety was 2. Therefore, the load is 720 kilonewtons. The allowable stress is 300 MPa. And if we transpose that and make the equation subject of A, we can find the area, which is 2,400 square millimeters. Look up in your one steel tables, look for an angle that has an area of 2,400 square millimeters, and you'll find that the closest one is a 125 by 125 by 12 equal angle with an area of 2,870 square millimeters, and that will satisfy that problem. Now, the one thing that I've just noticed, and as I always tell my students, this is my first mistake in 20 years. I'm only joking, of course. In question number 4, going back to question number 4, we had a factor of safety of 3. So we should have actually brought that into account here and selected a different universal column based on a safety factor of 3. But I might come back to you next time with the actual calculation on that in tutorial number 10, where I'll just do the revision of that particular problem. I apologize most profusely. Thank you very much, and I'll speak to you next time.